Hello, everyone. My name is Kwame Ade. I'm the founder and director for the Center for Operations Research and Data Science course. I double also as an assistant professor of business analytics at Minnesota State University, Moorhead. The objectives of today's video are first to illustrate entropy, the concept of entropy, and divergence for cybersecurity analytics using the R software. Specifically, we will conduct network traffic analysis using simulated data. We will focus on Shannon entropy and then Kullback Leibler and Jensen Shannon divergence. In addition to that, we will also employ the Jensen Shannon divergence to detect network traffic anomaly. So with that being said, we can jump straight into our codes. So before you run these lines of code, make sure you have these packages installed: the ggplot, the dplyr, the grade extra, and then the tidyr. So I'm going to simulate 4 scenarios. And then the 4 scenarios I'm going to focus on are first a normal traffic flow, and then a scan traffic, which is also known as the reconnaissance. And then I also simulate a DDoS traffic, which is the distributed denial of service. And then I also simulate a malware traffic. So if you see here, these are the probabilities of the true distribution. So we are assuming that P is the probabilities of each of the 4 scenarios from the original data. So 0.1 probability is associated with normal traffic, 0.2 probability is associated with scan traffic, DDoS traffic 0.3, and then malware traffic is 0.4. However, we also impose an assumption of distribution. So that is where we simulate a uniform distribution. So with a uniform distribution, we are assuming that each of the 4 traffic scenarios has a probability of 0.25. So then I attach the labels. So these are the 3. So if you see here, you see that we have those 3 showing here. So with that being said, I can compute the Shannon entropy for the original distribution. So in line 22, I compute the Shannon entropy for the original distribution, and then I print it out. So we are seeing it here. So it tells me that the Shannon entropy for this distribution or this simulated data is 1.846 and so on. So I can decide to let R to print it in the console for me. So when R prints it in the console for me, I see it here. So we are seeing a low Shannon entropy. So, and we know that Shannon entropy quantifies the unpredictability or randomness in a data. So this 1.846 entropy suggests that the data has some structure, but also contains irregular pattern. So if we see this original data, we are seeing exactly that we see some type of structure in here, but then definitely the pattern is also irregular. So what we can do is we can decide to look at the divergence between our assumed distribution and then the true distribution. So our assumed distribution is a uniform distribution. So we use the Kullback-Leibler divergence. So here I write out a function for the Kullback-Leibler divergence, and then similarly I request that it be shown here. So we are seeing that the Kullback-Leibler divergence is 0.15 as we see here. And this tells us that there is a low divergence between the two probability distributions. That's the assumed one and the one we imposed. I can definitely print it out as I did here, showing that also here. So one cool thing is I can print out those distributions and have their either Shannon entropy on there or have the KL divergence showing. So I plot a bar plot here. So I'm seeing the probability distributions for the four scenarios. So then the normal was 0.1, and then the scan traffic is 0.2, DD OS is 0.3, and then the malware is 0.4. And then it tells me that its entropy is this, which we computed. So this is a nice visualization for this simulated data. So I can go ahead to compare, and the comparison is definitely for me to be able to see how both distributions lie by each other. So this is for the uniform distribution and then for the true distribution. However, because this is overlaid, it's difficult for you to see it well. So what I'll do is I'll transpose the data using tidyr, and then when I transpose the data, I will go ahead and plot it side by side here. So I do a side by side plot, and now it becomes clear. So you see that the orange here is the imposed or assumed distribution for the four scenarios, and it is being compared to the true distribution. So this is a simple illustration of how we can use entropy and then divergence to uh, uh, see scenarios or traffic analysis in data. Now we can go ahead and then use the Jensen Shannon divergence to illustrate this too. So here I write the function for my Jensen Shannon divergence. And then following the same procedure, I'm seeing that my Jensen Shannon divergence is 0.04 here. And then what I want to do is I want to combine all three and then create a mixture of these distributions. So I do that here, and then I create all three. Then following that, I can plot the distributions here. So with the distributions, I'm seeing the true distribution being shown here. And then this is the uniform distribution. And this purple here is a mixture of my true distribution and then my assumed distribution, which is being shown here. So from this visualization, I can now go on and specifically use the Jensen Shannon divergence for network traffic anomaly detection. So I write my entropy function here, and then I compute my Kubark, or write a function for my Kubark-Leibler divergence, or the KL divergence. And then this third function, I write it for my JS divergence. So now I have them here. Now, because I don't have the real data, that is why I'm using simulated data. You can go to this website and you get some very good cybersecurity data. The name of the database is Canadian Institute for Cyber Security, and it has interesting data where you can see benign and malicious traffic with labeled flows. You can also decide to come to the MAWI working group traffic archive on this particular website, and definitely you can also get real world data. So I will continue with my simulated data. So for me to simulate the data, I set my seed here, and then I define the type of traffic for this data. So these are the traffic types. So HTTP GET, HTTP POST, HTTPS, DNS, SSH, FTP, and then other. So I call in my seed, and then I bring in the traffic types. So I'm only assuming that if you have the original data, you should be able to get the probabilities for these scenarios under what we will assume as normal traffic. So the line I'm writing here, I'm indicating that for normal traffic, HTTP GET has a probability of 0.35. And then still for normal traffic, order has a probability of 0.02. So I write and then that line, and then I further simulate other scenarios. So the other scenarios I have normal day. On a day there is a web attack. So on a day there is a web attack, what we are saying is that there is a high HTTP activity. That was the one that has the highest, which was 0.55 probability. Now, on a day of DNS tunneling, we see that there's unusual DNS activity, and this DNS, which corresponds to this DNS here, is 0.50. Similarly, we see that on a day that there is data X filtration, there is high post request, which is 0.45, and post request is the second one. Then finally, when we see port scanning, we see that on that day there is high unusual or unusual order traffic probability, which is the last one here. So that is the information we have. So based on that information, I can create a data frame with the scenarios and compute the Jensen divergence values using the function that I have. So that's what I do here. And now, the important thing is that based on this historical data that I have, I need to be able to categorize based on the Jensen divergence value that this is a low risk, medium risk, or high risk. So for my scenario here, I'm saying that if I get a Jensen divergence or JS divergence of less than 0.05, I'll consider it as a low risk. If it is between 0.05 and 0.15, I'll consider it as a medium risk. And then if it is anything above 0.15, I'll consider it as a high risk. So what I can do is I can decide to write that scenario here. So I've created a risk level categorization here. So now that I have that, I can decide to print network traffic anomaly detection. So we see that for a normal day, the GS divergence was 0.0019. And based on my categorization, this is less than 0.05. So there is a low risk level, which is rational because we created the data by ourselves. Now, when we look at on a day where there is a web attack, what we are seeing is that the GS divergence was 0.11. And based on my categorization, it's a medium risk level. However, on the day where there is port scanning, the GS divergence was 0.32. Now, based on the categorization, this is a high risk level. So it means I would have to probe further and see why that may have been caused. Okay. So what I may want to do is I want to create a comparison database so that we can visualize it because it's important for us to visualize this scenario. So that's what I do here by creating a comparison database. Then I go ahead and then I create the plots for the scenarios. So I combine these plots into a data frame and then I move ahead to run this. So once I've run this plot, I can now display all this in the grid. So I'd have to run my grid function before. So I have my grid library here. So I just run this grid library and then I come down and then call them in the grid. So finally, we are seeing that here. And of course, because the space is small, so it looks a bit clumsy. So what I'll do here is I'll zoom out and then enlarge this and share this with you. So you see, it looks better now. So now we are seeing, and of course, I want to move this down here. So we are seeing on a normal day, this is the JS divergence, and it is telling me that this is a low risk level. On a day of a DNS tunneling, this is the GS divergence. And based on the categorization, it says this is medium. When there is port scanning, this is the GS divergence, and it is saying this is a high risk. So the blues are the baseline, and then this gray color here are the computed. So we see for web attack, and then we see also for data exfiltration. So with that being said, it means we now know the JS divergence or Jensen-Shannon divergence for this simulated data. So if you do get any real world data, you should be able to get the probabilities from that data set. Thank you very much.